Hello and welcome to this GCSE Chemistry video about atmospheric pollutants. We'll begin by looking at what the atmospheric pollutants are that can form as a result of the combustion of fuels. And from there we will look specifically at how each of these can form during combustion reactions, what their properties are, and what their effects can be on both humans and the environment. From powering vehicles to heating our homes, fuels play a vital role in modern life, but their use comes with significant environmental consequences. The combustion of fuels is a major source of atmospheric pollutants. A fuel is a general name for something that we burn to release the energy stored inside. Examples of fuels include the fossil fuels, coal, oil, and natural gas. These are non-renewable fuels, or we might refer to them as being finite because they will eventually run out. Renewable fuels include bioethanol, biodiesel, and biogas, and these can be replenished to match the rate at which they're being used. Most fuels contain the elements carbon and hydrogen, and some fuels actually contain both hydrogen and carbon and nothing else, and these fuels are referred to as hydrocarbons. Sometimes fuels may also contain the element sulfur. The gases released into the atmosphere when a fuel is burned depends on the elements the fuel is made up of. Carbon dioxide with the formula CO2 and water vapour with the formula H2O are very common gases produced as a result of the combustion of fuels. Sulfur dioxide, SO2, and oxides of nitrogen can also be produced. Depending on the conditions present when the fuel is burned, carbon monoxide gas may be produced. In addition to this, we could release solid particles or unburned hydrocarbons. These last two may form what is collectively known as particulates. Combustion, which is also known more simply as burning, is a type of chemical reaction where a substance reacts with oxygen. Since it is a reaction with oxygen, we say that the element is oxidized as it is gaining oxygen. And the products of combustion are oxides of the elements that the fuel is made up of. Sometimes combustion can also be referred to as an oxidation reaction because the elements in the fuel are being oxidized. When there is more than enough oxygen for the combustion reaction to occur, we say that complete combustion is taking place. And this is when the fuel burns in a plentiful supply of oxygen. If a fuel is made up mostly of carbon, which is the case, for instance, with coal, the main chemical reaction will be carbon reacting with oxygen to produce carbon dioxide gas. And carbon dioxide gas, as we know, is a greenhouse gas. I explain greenhouse gases in depth in a separate video. If the fuel contains the element hydrogen, the chemical reaction will be hydrogen reacting with oxygen to produce water, which is not considered to be a pollutant. And so hydrocarbon fuels, which contain both carbon and hydrogen, will react with oxygen to produce both carbon dioxide and water, because carbon dioxide is the product when the carbon part of the hydrocarbon is oxidized in the combustion reaction, and water is produced when the hydrogen is reacting with the oxygen. For instance, if we have the hydrocarbon methane and it reacts with oxygen, we will produce carbon dioxide and water. And this is the case for any hydrocarbon, whether it is an alkane or an alkene. And you learn more about hydrocarbons in far greater depth in the topic about organic chemistry. In this topic, we will focus on the combustion of hydrocarbons when they are used as fuels. Now that we've covered how to write word equations for combustion, let's take it a step further by representing these reactions using chemical symbols in symbol equations. For instance, when we have the word equation carbon reacting with oxygen to produce carbon dioxide, we could use the symbols. Capital C for carbon, oxygen is a diatomic molecule with the formula O2, and carbon dioxide is CO2, which is a covalent simple molecule containing one carbon atom and two oxygen atoms. If we were burning hydrogen fuel, the word equation is hydrogen reacts with oxygen to produce water, but the symbol equation has hydrogen, which is a diatomic molecule with the formula H2, and oxygen again, and we produce water, which is H2O, which is a simple molecule containing two atoms of hydrogen and one atom of oxygen. Now, this second equation is unbalanced, and it's unbalanced because of something called the law of conservation of mass. Now, there's two crucial components to this. First of all, the law of conservation of mass dictates that atoms cannot be created or destroyed. And this equation looks like I'm trying to suggest that two atoms of hydrogen and two atoms of oxygen can produce water, which only has two atoms of hydrogen and one atom of oxygen. And so this cannot be the case. And the second aspect of the law of conservation of mass is that the total mass of the reactants must be the same as the total mass of the products. And so we need to go through the motions here of balancing this equation. Now, the rules for balancing equations are quite straightforward. There are two things. First of all, what you cannot do. You cannot change a formula. This equation would be easily balanced if I put a little 2 after the oxygen here and we make H2O2. But that changes the nature of water. Water is H2O. H2O2 is something completely different. And so to solve this, we can only have multiples of the reactant or product molecules. And so to solve this problem, we have not enough oxygen on the right-hand side, so we need to have a second water molecule. And so when we have two water molecules, as you can see I'm showing on the right-hand side, we have one oxygen atom in each of them. And so in two H2O molecules then, we do have the two oxygen atoms that we need. However, we also have 4 atoms of hydrogen. 2 from each molecule. And so where this equation was balanced before, it is now unbalanced, and so we need to put a 2 in front of the H2 because that means we have 2 times 2 atoms of hydrogen, which is 4. And so now this equation is balanced because of those big numbers we've put in front of the formulae, which are known as multipliers. If we look at the combustion of hydrocarbons now, methane CH4 reacts with oxygen O2, will produce carbon dioxide and water. Now we can see that this equation is balanced in terms of the carbon, but not balanced in terms of the oxygen and the hydrogen. In a situation like this, I always advise you to leave the oxygen until the end because it's occurring in more than one place in the products. And so first up, if we show the molecules with their bonds and their atoms on full display, known as their displayed formula, we can see that each molecule of water has 2 hydrogen atoms, and so to get the 4 hydrogen atoms we need on the right-hand side, we need to have a second water molecule, and so we put a big 2 in front of the water. And then now we can see that the carbon is now balanced, the hydrogen is now balanced, but the oxygen is not. In the 1 carbon dioxide molecule, we have 2 oxygen. In the 2 waters, we have a second 2 oxygen. So we have 4 atoms of oxygen on the right-hand side. And so to balance the reactants, we need to put a 2 as a multiplier in front of O2. And so now this equation is balanced. For propane, which is CCH8, that reacts also to produce carbon dioxide and water. This time, none of the elements are balanced. And so to balance the carbon, we need to have 3 CO2, because when we have that, we have the 3 carbon atoms that we need. To balance the water, we need 4 H2O, because once we have the 4 H2O, we have the 8 hydrogen atoms that we need. And so we've got a 3 in front of our CO2 and a 4 in front of our H2O as our products. Now, in terms of the oxygen, 3 carbon dioxide have got a total of 6 atoms of oxygen, and 4 H2O have a total of 4 atoms of oxygen. And so this gives us, in total on the right-hand side, 10 atoms of oxygen. And so to get 10 atoms of oxygen in the reactants, I need to have 5 O2 molecules, because each O2 molecule has 2 atoms of oxygen, so in 5 of them, I have 10 atoms of oxygen overall. So the full balanced equation for the combustion of propane is C3H8 reacting with 5 O2 to produce 3 CO2 and 4 H2O. Incomplete combustion occurs where there isn't enough oxygen available for a fuel to burn completely. During complete combustion, hydrocarbons react fully with the oxygen to produce carbon dioxide and water. However, in incomplete combustion, the reaction isn't complete, and other products such as carbon monoxide, carbon particulates, and unburned hydrocarbons can be produced. For instance, if carbon burns in the presence of oxygen and there is a limited supply of this oxygen, we might produce carbon monoxide. And so the symbol equation for this would be C plus O2 produces capital C, capital O for carbon monoxide. And so this equation needs to be balanced with a 2 in front of carbon monoxide's formula and a 2 in front of the carbon. If it is a hydrocarbon burning in the presence of oxygen, we would produce carbon monoxide and water. Notice that it is the carbon product that is affected by the limited supply of oxygen. For instance, if ethene was burned in oxygen to produce carbon monoxide and water, we would have the symbol equation C2H4 plus O2 produces CO and H2O. To balance this equation, we would need to put a 2 in front of the carbon monoxide to give us 2 carbon atoms on each side, and we would need to put a 2 in front of the H2O to produce 4 hydrogen atoms on both sides. And then we have got 4 atoms of oxygen in the products, and so we need to have a 2 in front of the O2 in the reactants, so we've got 4 atoms of oxygen there as well. If there is even less oxygen available for the reaction, the incomplete combustion reaction could produce carbon instead of carbon monoxide. And so, for instance, we might have methane reacting with oxygen to produce carbon and water. And the symbol equation for this would have CH4 on the left-hand side and C and H2O on the right, being formed after the reaction with O2. And so this is already balanced in terms of carbon. In terms of hydrogen atoms, we've got 4 on the left in the reactants, so we need a 2 in front of the H2O in the products. And in fact, this is now also balanced in terms of the oxygen. If we were burning coal, for instance, which is mostly carbon, what we would in fact be doing is simply not burning some of the carbon at all. So whilst some of the carbon might be turned into carbon dioxide gas and carbon monoxide gas, some of the solid particles of the carbon would simply not burn at all, but it might rise up into the atmosphere, being carried in the convection currents present in the gases themselves whilst they move away from the burning fuel. And this can also happen with other hydrocarbon fuels as well. Sometimes there is so little oxygen present in the fuel where it is being burned that some molecules of the hydrocarbon might burn completely, some atoms might burn incompletely, and some atoms may not burn at all. And so in all likelihood, there would be a mixture of complete combustion and incomplete combustion occurring, leading to a mixture of products. Incomplete combustion occurs when there isn't enough oxygen to fully burn the fuel, leading to the production of several harmful substances. Let's take a look at the key pollutants produced: carbon monoxide, carbon particulates, and unburned hydrocarbons. First, carbon monoxide. This is a colourless, odourless gas that is particularly dangerous because it's not easily detected by humans. This makes it even more harmful as it can build up in enclosed spaces without people realising it. When inhaled, carbon monoxide binds to hemoglobin in the blood more readily than oxygen, reducing the amount of oxygen that can be carried around the body. This can lead to symptoms like headaches, dizziness, and in severe cases, even death. Carbon monoxide is toxic and poses serious risks to human health, especially in poorly ventilated areas. Next, carbon particulates, or soot. These are tiny solid particles that are released during incomplete combustion. These particles not only cause severe health problems in humans, such as respiratory issues like asthma, bronchitis, and lung cancer, but they also contribute to global dimming. When these particles settle in the atmosphere, they can block sunlight, reducing the amount of solar energy that reaches the Earth's surface and affecting the climate. Finally, unburned hydrocarbons are molecules from the fuel that didn't burn completely and are released into the air. These hydrocarbons contribute to the formation of smog and ground-level ozone, which can irritate the eyes and airways and cause long-term respiratory problems. In summary, the products of incomplete combustion pose serious risks to both human health and the environment, making it crucial to minimise their production. In addition to the challenges posed by incomplete combustion, other pollutants can arise from impurities in fuels, like sulfur, which produces sulfur dioxide during combustion. When we burn fuels, they're not always pure hydrocarbons. Many fuels, especially those derived from crude oil, contain impurities, and one common impurity is sulfur. During combustion, sulfur reacts with oxygen in the air to form sulfur dioxide gas, which has got the chemical formula SO2. This reaction is especially common in fossil fuels like coal and oil, which can have a significant sulfur content. The process looks like this. Sulfur in the fuel reacts with oxygen to form sulfur dioxide. And so that's the word equation. The symbol equation is also quite straightforward. S, which is sulfur, reacts with O2, which is the oxygen, to produce SO2. And this equation is actually already balanced because we have one sulfur on both sides of the equation and two oxygen atoms on both sides of the equation as well. And while it might seem like just another gas being released, the presence of sulfur dioxide in the atmosphere can lead to further chemical reactions with wide-reaching consequences. And we'll dive into those specific problems caused by sulfur dioxide in a moment. Alongside sulfur dioxide, another group of pollutants can form during combustion, this time involving nitrogen from the air reacting under the intense heat of engines and power stations. Air isn't just oxygen. Around 80% of it is nitrogen, which is a diatomic gas with the formula N2. Under normal conditions, nitrogen is quite unreactive. However, when fuels are burned at very high temperatures, such as inside car engines, the heat energy provides enough energy to break the nitrogen molecules apart, allowing them to react with oxygen. And they produce a group of gases known collectively as nitrogen oxides, and they are given the formula NOx. These gases are collectively referred to as NOx because they include a variety of nitrogen-oxygen compounds, such as nitrogen monoxide, NO, nitrogen dioxide, NO2, and less commonly, compounds like dinitrogen monoxide, N2O. The simplest chemical reaction forms nitrogen monoxide, NO. And so the word equation is nitrogen plus oxygen produces nitrogen monoxide, And the symbol equation is N2 plus O2 produces NO. Now this equation has 2 atoms of nitrogen and oxygen on the left-hand side, but only 1 atom of each on the right-hand side. And so to balance this equation, we just need to put a large 2 in front of the formula for the nitrogen monoxide, and that multiplies both the nitrogen and the oxygen by 2. Nitrogen and oxygen could also react to produce nitrogen dioxide. The symbol equation for this has N2 plus O2 producing NO2. This is currently unbalanced for atoms of nitrogen, so we need to put a 2 in front of the formula for nitrogen dioxide. That gives us 2 atoms of nitrogen and 4 atoms of oxygen in our products. And so to get 4 atoms of oxygen in our reactants, we need to put a 2 in front of the O2. These reactions occur as side reactions during combustion and are more common in vehicles and industrial processes where temperatures are extremely high. Sulfur dioxide and nitrogen oxides are 2 major pollutants that can cause significant harm to both the environment and human health. Let's start with their impact on the environment. When these gases are released into the atmosphere, they can dissolve in rainwater to form acids. For example, sulfur dioxide reacts with water and oxygen to form sulfuric acid, while nitrogen oxides can form nitric acid. This leads to acid rain, which can damage forests, harm aquatic life by acidifying lakes and rivers, and it can even erode buildings and statues made from materials like limestone. But the problems don't stop here. For humans, both sulfur dioxide and nitrogen oxides are irritants that can cause or worsen respiratory problems. When inhaled, they can irritate the lining of the airways, leading to coughing, shortness of breath, and aggravation of conditions such as asthma. Long-term exposure may even increase the risk of chronic respiratory diseases. Reducing these pollutants is crucial, not only to protect our environment, but also to safeguard public health. You need to be able to predict the products of combustion of fuel when you're given the composition of the fuel and the conditions. So from the point of view of the composition, does it contain the elements carbon or hydrogen, or maybe it contains sulfur? If it contains sulfur, you need to be able to think, this sulfur will react with oxygen, and so sulfur dioxide will be produced. In terms of the conditions, maybe we are burning our fuel with insufficient oxygen or a small proportion of oxygen, and so we have to note that it will burn incompletely. Or perhaps we need to think about the nitrogen present during the combustion reaction, and so the very, very high temperature combustion will lead to the formation of nitrogen oxides during this process. You also need to be able to describe and explain the problems caused by increased amounts of these pollutants in the air. Now, precisely what you say will depend on how many marks there are available in the question. And so it could be a very open question asking you to explain the problem caused by an increased burning of coal. And so you might say that an increase in burning coal will cause more damage to buildings and to statues. This is a description of the problem. I've identified the cause and I've said an impact of it, but I haven't really explained it. That means I haven't really developed my idea and I haven't explained the connection between the cause and the problem. So an increase in burning coal will result in more sulfur impurities within the coal from burning and reacting with the oxygen. And so therefore more sulfur dioxide will be produced. And as a result of producing more sulfur dioxide, we will get more acid rain forming and more acid rain falling from the sky, and so therefore more damage to buildings and to statues. During my description and my explanation, you'll notice I used comparative language. I was using the word more a lot of the time, and you need to pay attention to things like that when you're answering exam questions. There are 5 main pollutants that you need to know about, and I'm going to summarise all 5 of them here, including details about where they come from and what their effects might be. First of all, we have carbon monoxide, CO, and carbon particulates, also known as soot. Both of these come from the incomplete combustion of fuels. That means where there is a limited supply of oxygen and we are burning the element carbon. Carbon monoxide is a toxic gas, and carbon particulates can cause global dimming and also health problems. Sulfur dioxide, SO2, is a pollutant formed when we burn sulfur impurities as a byproduct of perhaps burning a fuel such as coal. Nitrogen oxides, given the formula NOx, form when we are burning a fuel and producing a high temperature, and nitrogen from the air reacts with some of the oxygen present in this reaction. Both of these two fuels actually have the same effects. They are both contributors towards acid rain, and both of them can cause respiratory problems in humans. And finally, carbon dioxide gas, CO2. This is formed as a result of a fuel containing carbon burning in a plentiful supply of oxygen. Carbon dioxide is a greenhouse gas, which means it can contribute to global climate change, which can have a number of effects, which I detail in a different video. Okay, that's the end of this video. Thanks for listening.